Well, hello. We're going to be talking about light today. Now, we think about light in lots of different ways. There's some big objectives here we can look at. I'm not too concerned about those right now. I want to get right into this. So let's hide this here. So when I think about a stove, an electric stove like this, if the lights went out and for whatever reason the stove was still on, it would emit light, even though the purpose of a stove is to give heat. On the other hand, I've got a light bulb over here, and its purpose is to give off light, but it gives off a tremendous amount of heat. So we can think about, the efficiency of these different appliances, but fundamentally, what is light? What causes us to see light? That's what we want to talk about. So in both of these, most of the energy being released is in the form of heat. Nowadays, very few people use these filament light bulbs. Instead, we use LEDs or other things that are much more energy efficient, fluorescent type light bulbs. How does a light bulb work? Well, it has in there different filaments. That was really exciting. So in a tungsten light bulb, you have in here a metal, tungsten, has the symbol W, and when you shove too many electrons through, the electrons rub against each other and they glow red hot. So I have two different wires here. I've got here a very thin wire and here a fat wire. So it might represent a 12 gauge wire and an 8 gauge wire. Okay. And if I were to try to push electrons through, these can get through pretty well. And you see these have a lot more space, so I can put more electrons through here without them rubbing on each other. So if you have a thin extension cord and a fat extension cord, the fat extension cord is going to do a better job of staying cool. Now, if you're in college and you're in a dorm, you might have a extension cord with 4 different things running on it, and you bury it under a carpet. That can be very, very dangerous. So my advice to you is buy the best heavy-duty extension cords you can afford, and they will serve you well. Now, in terms of a light bulb, we want the light bulb to have very thin wires in the filament so that it glows red hot. In a fluorescent light bulb, you actually coat the glass with a phosphor, zinc sulfide, and the electrons are trying to jump from one electrode, let's say on the left, to the other on the right. And they can't quite make it all the way across, so what they do is they end up striking the surface and it glows. And that's what causes that fluorescent light bulb to glow. If a fluorescent light bulb is on and you touch it with your hand, it's really not very warm. And that's because most of the energy is going to form light. So when the electron jumps up to what's called an excited state and falls back down to the ground state, it releases energy. And we'll talk more about excited states and ground states in this lesson. All right, let's keep moving here. So I've got here an atom. I'm looking at the cross section. Here's the nucleus, and I'm going to go ahead and put in 3 electrons. So that must be, if it's an atom, that must be a lithium atom. So it'd be a 1s2, 2s1. And ground state refers to the electrons as close to the nucleus as they can go. In other words, we've used the right filling order. Now, what can happen is this electron in the second energy level can absorb energy. So this HV, think of that as energy. And it takes that electron and it moves it up to a higher energy level. So now this might say, as an electron configuration, 1s2, 5p1. And clearly that's out of order, but we call that an excited state. An excited state atom. Now, it can't, of course, stay in the excited state forever, and it ends up falling down. And as it falls back to the ground state, it's going to release energy. And it's going to release energy in the form of light. That's why you see light. Electrons get excited, they lose their excitement, and they fall back down. Now, in the case of this last example, the electron gains so much energy that it's simply swept off of the atom. So it's completely removed from the atom. We call that ionization. An ion is formed. So in this case, the lithium atom lost an electron and has now formed a cation. Okay? That electron is not going back to that atom. It's been completely removed. Now that's a little bit different than an excited state. In an excited state, the electron just moves from one level up to a higher level, but it stays on the atom. All right, we got some humor here. Haven't had humor for a while. Here it is. Here's the question. Why does hamburger have lower energy than steak? And the answer, as you might know, is because it's in the ground state. Not very funny. All right, so let's define some terms here. We've talked about photons, little bundles of energy, right? And it turns out that energy is, we think of as kind of like a currency, where in American currency, we have a penny, a nickel, a dime, a quarter. And it turns out that particles, these bundles of energy, only come in certain allowable energies. It's not continuous, but instead it's discrete. So electrons can go from one level to another, but they don't stop in between. And we'll talk a little bit about light as a particle and as a wave, and then recognize it actually has both this particle-wave duality. Both are actually correct. Now, you've all seen, maybe you've been to the ocean, you see the waves, they go up and down, right? Maybe a seagull lands on there, so it goes up, and then it goes down, and it goes up. And really, it's the wave going up and down and up, and the seagull is really in a stationary position. Now, a wavelength, this is a symbol for wavelength, it's lambda, would go from a crest to a crest, or a trough to a trough, or when it repeats itself. That's one wavelength. So we can see here, there's one wavelength from here over to here of our ocean waves. All right. When you take physics, you get to play with prisms and do cool stuff, right? If we look at white light and pass it through a prism, what happens is that white light fans out into the rainbow. So we get different wavelengths of light. So here in this experiment, light is looking as different waves, isn't it? Okay. Now, theoretically, I suppose if you took two prisms and inverted them, you could put white light in, it would come out as a rainbow, and then that rainbow would go back in through the prism and come back as white light. I'll let you ask your physics teacher to demonstrate that one for you. All right, maybe some of you play the guitar and you recognize that if you pluck the string, you can get a half a wavelength. That's a pretty deep tone. And if you put your finger halfway in between here, the tone gets much higher. And as you shorten the wavelength, you get a higher tone, a higher frequency. So here we have a half a wavelength. Here we have one full wavelength. Here we have one full wavelength and another half, right? So 3 half wavelengths, or 1.5. And you can kind of see us strumming those waves if we wanted to. All right. We talked about in chemistry that those wavelengths have to be just the right amount of energy. So when it goes around, it has to sink back exactly 4 times around, or 6 times. It's not going to be 4.2 times. It's not allowed in chemistry. All right, so let's define some terms. Wavelength, the length of one complete wave. It's the symbol lambda. Frequency, textbooks use the letter nu. It looks like a cursive V for the number of waves that pass a point during a certain period of time. It's measured in units of cycles per second, or hertz, H-E-R-T-Z. And the amplitude of the wave is how high the wave is, right? Is it a 10-foot ocean wave, or is it a 2-foot ocean wave? That's the amplitude. And both frequency and amplitude have to do with how much energy is in that wave. Now for our class, I will simply use F for frequency. I think a lot of teachers actually do that. So let's look at this wave here. All right, so we've got a crest here, the top, the trough is the bottom, the origin is that midpoint that it would start with. Here's the wavelength, crest to crest, origin to origin. Here's the amplitude, from the origin to the top, from the origin to the bottom. That's the amplitude of the wave. Now, between these two waves, which one has a higher frequency? Well, before you tell me the top one, understand frequency is how many waves happen per unit of time. So if we start here and end here, and that's 1 second, I get the same exact amount of waves. So they actually have the same frequency, but the top one has a higher amplitude. It would take more energy to create the top wave than the bottom wave. So greater amplitude, it would be a more intense sound. Okay. Now between these two, the yellow and the blue, can you see that the amplitude is actually the same on these? If you hold your finger up to the screen and measure, you notice that this height and this height, they're the same. But the bottom one, you have more waves per unit of time, right? Here we see only 2 peaks, here we see 3. So the bottom one is a higher frequency. And so when you look at colors like red, orange, yellow, green, blue, indigo, violet, red is a very long wavelength, low frequency, and violet will be a high frequency, high energy wave. All the colors that we see fit on what's called the electromagnetic spectrum. Now, we only can see a very small region, the visible light, and we use Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, to represent those colors. But when an electron moves, it creates a magnetic field. Now, some of it we see, that's visible light. Some you don't see, like when I go outside, the ultraviolet rays gives me sunburns. Or maybe you get an X-ray. You can't see them, but the film can certainly see them. That if you do an X-ray, right? Infrared is heat. So that's what police use and military uses to see people at night. And then, of course, you have radar waves and radio waves, right? Like in your home, there are radio waves going through. You can't see them, but if you have a radio and turn it on, the radio can see them. So it turns out that if we were to draw the waves here, the really long waves are on the left side, radio waves, gravitational waves. Visible sort of in the middle, and then X-rays and gamma rays are really, really short, short wavelengths, very high frequency. Now, it turns out that anything above visible light is what's called ionizing radiation. It knocks electrons off atoms and causes damage. Anything visible and less is not ionizing. Perhaps you have a black light in your room, and if you ever looked at it, it looks kind of purple, doesn't it? Because higher energy than violet is ultraviolet. Now, your eyes don't have very many pain receptors in it, so if you're staring at it, you're actually damaging your eyes, but you don't know it because you don't feel the pain. And it does show a little bit of the violet color, but most of that energy is in the ultraviolet region, and you can't really see it. So let's talk about frequency, okay? I said it's cycles per second, so I mapped out 1 second of time. Now, if we make this 1, 2, 3, 4 cycles per second, right? That has a frequency of 4 hertz. This next one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cycles per second, or 12 hertz. And this last one, I'm going to let you count it. Ready? Get set, go! 36 cycles per second. Okay? Can you see the last one is the highest frequency? Now, if this was a spring and you were trying to shake the spring, it would take an incredible amount of energy to make this very high frequency light here. Much more energy. Now, I want you to think about colors of lights. If it's a foggy day, there's water, that's little spots all over the screen. And most of those spots would miss completely the red line, which means red light goes through fog. Now, fog lights tend to be orange because we need red for stop signs and brake lights, and orange are the color of fog lights because they go through most things. White light, the color of your lights on your car, are the combination of all of these. See how close these wavelengths are together? That means if there's dots of water, they're going to get hit by the light and get diffused. And that's why light doesn't go through fog very well. Now, that poor old dog, dogs have great hearing, don't they? They can hear in very high frequencies that we can't hear, right? You can take a dog whistle, you can blow it, you can't hear it. You know, maybe you have a mosquito ring phone on your phone. where if you're 30 years or younger, you can probably hear it. If you're over 30, you can't hear it because of hearing damage, right? So sounds have different frequencies. That's something we should be familiar with. Now, maybe you've heard of AM and FM radio, but you didn't really know what it stood for. So let me help you out there. AM stands for amplitude modulated, and FM, frequency modulated. So this might be a sound pattern of me clearing my throat like that. Now, if I were to put that on amplitude modulated, it'd be and we can kind of see that sound, right? So the amplitude goes up and down. Now, if this were FM, it would look like this, right? And notice that the frequency gets high frequency, low frequency, high frequency, but the wavelength doesn't change. Now, it turns out it's less expensive and easier to make AM waves than FM. So there's a lot of talk radio on AM. And where do you find the better radio stations? Well, they're generally on the higher number of the dials because it takes more energy to generate a higher frequency wavelength. And so therefore you better play better songs, have better DJs and so on to get better advertisement to pay for all that. So the carrier frequency is like 101.2 or 98.6. That's the frequency you're talking about on FM. All right, enough on that. Let's see here. Well, I want you to notice that in terms of the electromagnetic spectrum, visible light is roughly in the range of, let's say, 400 to 700 nanometers. That's the wavelength that we can see. Wavelengths that are longer than 700 nanometers are going to be infrared microwave radio. Wavelengths shorter than 400 nanometers will be in the ultraviolet region, X-ray, gamma rays, things like that. Now, these numbers, we're going to get into these numbers a little more later. For right now, I'm just going to leave that one. You'll have some homework related to that later. Okay. There's nothing that I need you to know on this slide. I'm simply giving you an order of magnitude. A radio wave is approximately a meter long. Microwaves are roughly, on the order of a centimeter long. That's why you have that little metal screen in the glass in front of the microwave with the small holes in it. The microwaves cannot pass through those small holes because their wavelengths are too large. Infrared is on the order of millimeters or micrometers. X-rays into nanometers, and you can see how small gamma rays are, 10 to the negative 12 picometers in terms of size. All right, let's play a little game here. I've got a low frequency red wavelength and a higher frequency green wavelength. Now, we said that light could act as waves or as particles. So I'm going to show you it both ways here. So the first thing I'm going to do is we're going to have a race. I've got a little photon here, a red one and a green one, and they each have to stay on the path, and we want to see which one gets from the far left to the far right first. Now, I think you might know the answer. If you think it's the red one, let's see if you're right. Ready, set, go! Well, what should have happened is they get there at the same point. All light travels at the same speed, the speed of light, 3 times 10 to the 8th meters per second. So clearly the green guy had to be really moving around fast, but in terms of getting from left to right, how fast it really went, it was the same speed. Now, if you happen to be standing here on the red line or standing here on the green line and you got bumped by the red photon or bumped by the green photon, it would have hurt more because it packs a bigger punch. It's a higher frequency of light. Okay. Now, we could try it one more time to see if it was a fluke. Nope, it wasn't a fluke. Every time it's going to be the same. Now, what I'm doing now is I'm counting up. Maybe you got to summer camp and you had to do those friendship beads. So I'm putting little beads, little photons, little bundles of energy on each. And now, oops, you forgot to tie a knot and all those little beads fell off, right? You got to pick them up off the floor. So it turns out the top one had 60 photons, 16 beads, and the bottom one 162. And maybe those beads represent energy. Can you see how now there's much more energy packed into green light than in red light? So I'm trying to show both the idea of a photon, those little bundles, and wavelengths as ways to represent energy. Other ways, so in other words, red is low energy, green is higher energy. If I had a blue line, what would it look like? Well, it would have more peaks, and they'd be even closer together than the green because it'd be higher frequency. Another way, here's the way this author does it. They make their photons, little bundles, bigger. So notice that there's little red balls here and bigger ones here. These are packing a bigger punch, bigger photons, higher frequency. We can think of it either way. That's okay. And again, what is a photon? It's a particle of light that carries a bundle, a quantum of energy. Like there's a penny, a nickel, a dime, a quarter. Each is a coin, but they have different numerical values, different cash values. So we can think of light as a wave or as a particle. And it turns out we have experiments that show it as both, but no experiments showing it as both simultaneously. I put this on here. If you have ADHD, you can sit there and play this part of the video over and over again and watch the little bead go up and down, back and forth, back and forth. I wouldn't. I just keep moving though. All right. Now let's get into some calculations. All right. So here we go. We got this weird looking formula. C equals, well, remember this nu was actually frequency times wavelength. So I'm going to put this in here. C is a constant. That's why it's a C. It's constant. It's the speed of light. It's the ultimate speed limit, 3 times 10 to the 8th meters per second. If you're wondering, that corresponds to about 186,000 miles per hour. Frequency is your cycles per second, or hertz, and wavelength always needs to be in meters for this to work out unit-wise. Okay? Now, it turns out that nu, this frequency, is related to energy by Planck's constant, which is h. So here, E is energy measured in joules, h is another constant. It has a numerical value of 6.6 times 10 to the negative 34th joules per second. And I'll give you that. And of course, frequency is your hertz again. Now, I'm not going to show you on this sheet of paper, but I could easily solve this first one for nu. Nu would be, if you solved it, C over lambda. Then for nu, I could put C over lambda, and I would get, I'm just changing those to frequencies, I get this formula down here. Energy is equal to Planck's constant times C over wavelength. Now, you don't need to use the last formula there. You can use these two, or a lot of students like to use the last one as well as these two. It's your choice, okay? And you have a little homework related to that probably tonight. All right, so let's do a question related to this. Find the frequency of a photon with a wavelength of 434 nanometers. So what do we know? Well, we know we're looking for the frequency, and we know the wavelength is 434 nanometers. Now, remember we said that that has to be in meters, so we need to do a conversion. Perhaps you remember there's 1 times 10 to the 9th nanometers, that's a billion, per meter. So that unit cancels out, and we're left with 4.34 times 10 to the negative 7th meters. The speed of light is a constant, 3 times 10 to the 8th meters per second. Use that value unless told otherwise. So our work for this, remember, well, this isn't right because it should be C equals F times lambda, right? So I think there's a little error on that slide. So how about this? When you solve that, C equals F lambda, you get frequency equals C over lambda. That sounds a little bit better to me. Now we can put in our values. Frequency is equal to the speed of light divided by the wavelength. Notice that meter cancels like that, and you're left with a unit of 1 over a second. 1 over a second, isn't it, right? And that is a frequency of hertz. So the frequency of a photon of a wavelength of 434 nanometers is this right here, 6.91 times 10 to the 14th. That's the kind of math you'll have to do in this unit, All right. I'm not going to talk about the ultraviolet catastrophe right now. I'm going to skip all that stuff and call this one done for right now. It's a short little 25-minute lesson. Hopefully that made some sense to you, and we'll stop right here. So thanks for joining me, and have a good one.